Good day. Welcome to the Physics Exercises channel. We are going to solve a problem which involves kinetic friction on a rough incline. So the problem, which I will read, is from Serway and Jewett, actually. It's chapter 7, so it's energy, and the chapter on kinetic energy, I believe. We have a crate of mass 10.0 kilograms is pulled up a rough incline with an initial speed of 1.50 meters per second. The pulling force is 100 newtons parallel to the incline, which makes an angle of 20 degrees with the horizontal. The coefficient of kinetic friction is 0.400 and the crate is pulled 5.00 meters. Okay, let's, before we go into what are the questions, let's draw a picture of what's going on. Okay, so let me go and make myself a pen, okay? And we have a crate of, so I will first draw the incline and then the crate. I think that makes sense. That should be the incline. Okay, maybe not very straight, but I'm trying. And this is 20 degrees, 20.0, but okay. And here's our crate, and it's being pulled up. Okay, and this force is 100 newtons, so it's given here. And an initial speed of 5 meters per second. Okay. So let me also write that we have a mass of 10.0 kilograms, an initial speed of 1.50 meters per second, and the pulling force is 100 newtons, and it's parallel to the incline. The coefficient of kinetic friction, okay, so we need that too, so I'll write that here as 0.400. That's not a nice mu, but okay, I think I fixed that, because this is all the initial data we have. And the crate is pulled, that's also important, up some distance d, and that distance is 5.00 meters. Now, before I go on, let me just state that for simplicity, I will use g equals 10 meters per second squared, not 9.8. Okay, so if you want more accurate results, redo the calculation with 9.8. Okay, especially if you plan on doing this experiment and checking the results, which is something I strongly encourage. Okay, so how much work is done by the gravitational force on the crate? We can answer this actually just by looking at it, but I want to work it out in detail. We know what the gravitational force acts downwards, and the component of the force that acts upwards works against gravity. So we can calculate that like that. So you could say that the displacement, okay, so the displacement is actually 5 meters, but what you need is the component of the displacement in the direction of gravity. So that's actually d sine 20. Sorry, d sine 20. D sine of 20 degrees. Okay, so that's the height that it goes in the vertical direction. This here is d sine 20. Okay, and so that's actually the height, the change in height of the object, you might say. And so mgh will give you the work done, well, actually minus mgh will give you the work done by gravity. Okay, so you can read that off, and that's easy, but let me actually be a little bit more detailed and be a little more specific. Let's draw a free body diagram and solve this problem in detail. Okay, so I'm going to scroll a bit. So free body diagram. Okay, so here's my object, and it has the following forces acting on it. The point represents the object. So I have, on the one hand, I have gravity. I also have the normal force acting this way. I have the force pulling the object acting this way. And I also have the friction force acting opposite the sense of motion. Okay, so these are all the forces I have. And it's obvious that in order to get equations of motion, it's probably wise to use the coordinate system, which is like this. Okay, so I mean, in terms of the incline, going back to this figure that I drew, that's the x direction, which is parallel to the plane of the incline. And that's the y direction, which points away from the incline. Okay, and the reason that's the coordinate system you want to use, because then you only have to break one of the forces up into components, right? So, for example, if you used this coordinate system, the usual one, x, y, you would have to, well, mg is the y component of this force, but all the other forces have to be broken up into components. So you don't want to do that. You want to use, it's simplest to use this particular coordinate system. Okay, so based on this coordinate system, we can write now equations of motion. Okay, so in the x direction, we are going to have, and I'm taking upward, so going this way as the positive direction, and we are going to have capital F minus small f, but that's not complete, right? Because we need mg, we see that mg has a component in that direction, but let's investigate. So I'm going to redraw the incline again. Okay, so we have a triangle like this. Okay, and here the angle is 20. Okay, but we can also draw a triangle like this. And that angle in there would also be 20, right? That's a similar triangle to the first one. And you see that this component is actually minus mg sine of 20. And that's actually consistent with our first guess for the answer to this problem, which is actually, so this is the correct answer, but I'm working it out in terms of a free body diagram to give more detail into this solution. Okay, so based on this free body diagram, the information we obtained so far is F minus mg sine theta is actually equal to the mass of the object times its acceleration, which we don't know at this point. Okay, so that's one equation that we can derive from the free body diagram. Now I keep going. In the y direction, what you have is, well, n minus the other component of gravity. Okay, so this here is gravity, and we already used this component. It's actually this component that we need, minus mg cosine of 20, okay? And this is equal to 0 because the object is not accelerating in the y direction. That's the other reason you want to reuse this coordinate system, because then you only have one non-trivial equation to deal with, okay? But most importantly, what this equation actually gives us is the normal force. because we can read from it immediately that the normal force is mg cosine of 20 degrees. Okay. And since we now have the normal force, we also have the friction force. Let me scroll and write now that the friction force, the magnitude of the friction force, so actually notice that here, this is a magnitude, this is a magnitude, this is a magnitude. These are all magnitudes. And the direction of the forces is taken into account by the signs in the equation. So here F is positive, it's in the positive direction, minus F is negative, it's in the negative direction. Okay, so that's an important detail in setting up the equations of motion using the free body diagram. Okay, so I'm going to write here the definition of the friction force, because it's none other than mu k times the normal force, and it's mu k mg cosine of the 20 degrees. Okay, so that is our friction force. I did not write the 20 with the significant figure, so actually the 20 really should be 20.0. Okay, but yeah, so I saved a little of space that way. Okay, so we have all the forces that we need. Okay, we have all the forces that we need. Now let me go back and try to answer the actual question. So first is how much work is done by the gravitational force on the crate. Okay, we calculated that already. Determine the increase in internal energy of the crate incline system due to friction. Okay, so for that actually we do need this. Okay, so let me for part A, we found that the work done by gravity, there should be no equal sign there, that was a mistake. The work done by gravity is minus mgd, those are all numbers, times the cosine of 20.0. Okay, so that's one answer. Okay, now for question B, we want the work done. Well, actually, it's the energy dissipated. I think that's the way the question is phrased. So let me reread it. Determine the increase in internal energy of the crate incline system due to friction. And what they mean by that is let me actually just go back to this picture that I drew. As the crate slides along the incline, okay, so as the crate slides along the incline, it generates friction. It generates heat, actually. As it slides around the incline, this part of the crate also here, and the incline is getting hotter, you might say. And that can be calculated because the work done by friction goes into increasing the internal energy of the crate incline system. Okay, so for the second part, we have the force, okay, and we also know, so the force was mu k mg cosine 20. Sorry, I did that wrong. Let me. Okay, and the work done by friction is going to be just F times D. Okay, so the point is that, well, we can actually write a simple we could write a simple formula for it even in terms of the gravity, right? But basically it's, and sorry, actually there's one little mistake that I made here, that this is minus, and that's because if we go back to the picture, we see that the displacement is upwards, but the friction force is acting downwards. We see that here, right? So this is certainly acting downwards, so this should be negative. So basically, what we find is minus mu k, and we can calculate all of this at the end, mg d times cosine of 20. Okay, so that's the work done by friction, which is also the increase in internal energy of the system, of the crate and incline system. See how much work is done by the 100 Newton force on the crate. Well, that's easy, right? The 100 Newton, because we know that the force is 100 Newtons, and we know that the displacement is 5 meters. Okay, and I'm going to denote this W capital F. That's F times D. So we can calculate it when we need it. Okay. I didn't give numbers yet. I will do that at the end. Okay. But in any case, that's the work done by the pulling force. And now I go back and I read the other questions. What is the change in kinetic energy of the crate? Okay. The kinetic energy of the crate changes for several reasons here. First of all, we can say that, so D, the change in kinetic energy, of the crate, let me indicate that by delta K. And of course, we know from the work energy theorem that the work done on the crate goes into its change in kinetic energy. But how much work is done on the crate? Well, all three agents, so the force WF does work on the crate, the friction does work on the crate, and the gravity does work on the crate. And all three of those we already calculated. Okay, so we can go back and calculate that when we need the numbers. But the idea is this. And notice that this is positive. And I didn't say that, I didn't explain that in detail, but you know that because this F here is parallel to the displacement. Okay, so friction acts opposite the displacement, but capital F is in the same direction as the displacement. So that's positive work. On the other hand, friction is negative because the friction acts opposite to that displacement, and gravity, the component of the gravity, which is in the direction of motion, is also opposite the sense of motion. Let's go back and see why that is. This is gravity. It has a component this way and a component this way. Okay, and this component is opposite the direction of motion, so that will also be negative. That work will also be negative. Okay, it turns out that this component of gravity does no work, and neither does the normal, because those two forces are, or one component and one force rather, are perpendicular to the displacement. Okay, and now last question, what is the speed of the crate after being pulled 5.00 meters? And you can calculate that by doing the following. So if you have delta K and you have Ki, and Ki is not given, but you can calculate it because it's the mass of the object times the initial velocity divided by 2. And of course, you know that K, the final kinetic energy, is Ki plus the change in kinetic energy, which is m over 2 V F squared. So you can put this together and calculate it. But now let us do the numbers. Okay, so what do we need here? Okay, I might not go in order, but let me now do the numbers. Okay, let me actually fix one that my K doesn't look very nice, so I'll fix it. So this is the final kinetic energy Kf. Okay, so let's first do Wf, that's easy. So W capital F is, well, that's easy, right? Because it's 100 times 5. So that's actually 500 newtons. What is Wg? Let me calculate that. Let me go back and check what it is. It's minus mgd cosine 20. I forget what the mass is, so I have to check it. The mass of the object is 10 kilograms. Okay, so this is minus mgd cosine 20. which is minus 10 times 10 times 5 times cosine 20. And I have to do that with the calculator separately. Okay, so 10 times 10 is 100. That makes, so there's going to be a minus 500 times cosine 20. Sorry, I will give you the number shortly. Okay, so I just have to go to my calculators. So I just need the cosine 20, really. Okay, so cosine 20 is about 0.4, 0.41 maybe. And I'll multiply that by 500. So I get about 204. Sorry, there's 204. Sorry, this is not newtons. This is joules. Apologies. I made a mistake in the unit, so let me fix that. But it's so it's. Let me write this number first and then fix that mistake. So this here is not newtons; it's joules. Sorry. This is joules. Sorry about that. And the number I obtained for 500 times cosine 20 is about 204. Okay, so this makes 204. But it's actually minus. Okay, let me write that a little bit clearer. Wg is equal to minus 204 joules. And then there's actually a simplification which I will use here. If I go back to my friction, I see that gravity is minus mgd cosine 20, right? And my friction is minus mgd cosine 20 times mu k. So I see that the friction is actually mu k times the work done by gravity. So the work done by friction is mu k times the work done by gravity. Okay, and if I go here, I can write that this is minus 204 times, I forget what the kinetic friction coefficient is, so I go back and look it up. It's 0.400. Okay, so I have to use the calculator again for that. Okay, so 204 times 0.400 is about 82 joules. Okay, so that's going to make 82 joules. And it's minus. Okay, so now we know that the total work done on the object, the total work, is going to be the 500 minus the 204 minus the 82. And that's going to be in joules. Okay, so how much does that make? 500 minus 200 is 300, 296, 216, 214 joules. Okay, so, so in lifting this object, this is the work we had to do against gravity, and this is the work we had to do against friction, okay, which was dissipated. Okay, you can recover the one from gravity by letting the object slide down the incline, okay, but you will again use exactly the same amount of friction. But what happens to the kinetic energy of the object is what we are trying to calculate. So we calculate the initial kinetic energy of the object. So the initial kinetic energy of the object is the mass, which is 10 kilograms, divided by 2 times the initial velocity, and we have to square that, but I forget what the initial velocity is. I'm going to go back and look at it. It's 1.50 meters per second. So if I square that, I get 2.25. So I have here 2.25. Okay, so that's actually 5 times 2.25. which is actually 11.25 joules. Okay, and from this, we get that the final kinetic energy is going to be, well, okay, I'm going to round this to 11. Okay, so it's going to be 215, 225 joules. Okay, and this is m over 2 final velocity squared. Okay, so it's actually Vf is the square root of 45, I think, right? So let me just do that again. 225 times 2 is 450. I divide it by 10. I get 45 for Vf squared. What is that about? Well, you can simplify that to 3 square root of 5 meters per second. Okay, and that's actually only approximately true. Okay, but actually you wouldn't leave it in this case in that form because everything here is approximate. And so you would have to calculate 6.71. So the final velocity of the object, it turns out after a calculation to be about 6.71 meters per second. Okay, so that would be the solution of this problem. Thank you very much for your attention. All the best. Have a nice day.